Hello everyone. In this video, I will introduce a new image descriptor for scene recognition tailored toward natural environments. In robotics, this task is used for most large-scale SLAM systems for the loop closure step. It is also useful for long-term monitoring systems operating outdoor. The challenge in long-term scene recognition is the variations of appearance in the scene. One example is seasonal changes. To remedy that, I propose to describe images with their semantic edge information. Edges are one of the most invariant elements in the images, so this allows for robust image description. In the rest of this video, I will first briefly recall how image descriptors are used for scene recognition. Then, I will introduce my novel descriptor, dubbed WASABI, and in the last part, I will compare it with related methods on natural scene recognition. Scene recognition is the process by which a place that has been visited in the past can be identified when visited again. Images from the past are stored in a database. When a new place is visited, the corresponding image, that I will call here the query image, is compared against the stored images. Database images with the most similar to the query are retrieved. The comparison between database and query images is not derived directly on the images, but on their descriptors. A descriptor is a numerical vector representation of the image. It is defined so that images with the same content have similar descriptor. Conversely, images depicting different scenes should have different descriptors. This way, scene recognition amounts to simply measuring the distance between descriptors and retrieve the images with the nearest ones. The main challenge is to define descriptors that depend only on the structure of the scene and not the appearance of the scene. For example, here, the two images associated with the blue and the purple descriptors depict the same scene as the query image. However, the blue image and the query image do not have the same appearance because of a change of season. The contribution of this paper is to define a descriptor that is invariant to these appearance variations. WASABI operate on semantic edges. Two images match if their semantic edges are similar. To assess edge similarity, I compute a canonical representation for each edge. Then, I compute the distance between semantic edges with the same level, and the distance between images is the sum of the distances between matching edges. The canonical representation I use is the decomposition of the edge over a basis of wavelet functions. A given edge is modeled by a parametric curve C, which is a discrete function here. The edge is subsampled over a fixed number of points n, which is a parameter of the method. I split the curve over its x and its y axis, and this defines two discrete functions. I decompose each of these functions over a basis of wavelet function. For example, here, the cx function can be written as a linear combination of these wavelet functions, and I store the even coefficients of this decomposition. The edge is then characterized by the concatenation of the x decomposition and the y decomposition. In the experiments, this vector has a size of 128. Now on to the evaluation. Scene recognition is evaluated with the recall at n that represents the ratio of query images matched within the top n retrieved images. The evaluation is run on two outdoor datasets, the Symphony and the extended CMU datasets. The Symphony one depicts images sampled for 4 years along a lakeshore by an autonomous boat. Images mostly hold vegetation. The extended CMU-Seasons depicts area from Pittsburgh, and I use two splits, the park one and the city one. The park split mainly shows vegetation, whereas the city one shows both vegetation and building. I compare WASABI to other semantic-based recognition methods. The first one is the lost descriptor that aggregates deep features of pixels with static semantic classes in a VLAD fashion. The second is the Toft descriptor that concatenates both gradient histograms and semantic histograms over local regions of the image. The resolution of these regions is a parameter that highly influences the performance of this descriptor. The final baseline is VLAS that also leverages semantic edges and aggregates deep features of edge pixels in a VLAD fashion. Now onto the result. This plot shows the retrieval performances over the 3 types of environments, and I will now go through the main observations we can draw from this plot. The first one is that learn-based descriptors are better than handcrafted ones. Here, the lowest results, circled in red, correspond to the back-of-words and VLAD methods derived with SIFT descriptors. The second observation is that semantic-based approach compare with state-of-the-art deep methods such as DELF and NetVLAD. And this is an interesting observation because it shows that the manual integration of semantics is a relevant alternative to training a network specifically for recognition. One method clearly presents an advantage over the others, and this is the Toft descriptors computed over fine regions of the image. The performance of this method heavily depends on the resolution at which local regions are described, and although the finer resolution induces a higher memory requirement, this can easily be overcome with dimensionality reduction. As for WASABI, on natural environments, it also offers an advantage over previous semantic-based methods, although smaller than the Toft descriptor, and it generalizes well to urban scenes and reach near state-of-the-art performance. However, it is very sensitive to the segmentation noise. The segmentation used in the experiments is tuned for the CMU-Seasons data, but not for the Symphony data. And although the segmentation can quite generalize, it is noisier, and this induces a degradation of 30% of the performances for WASABI. To compare with the other methods, they degrade only up to 10% of their original performance. The main takeaway from this video is that semantic-based image description compared with specifically trained descriptors. Also, semantic edges provide information relevant enough for image description. However, we saw that WASABI is too sensitive to the segmentation noise, and this limits its application. If a segmentation network for a specific dataset is not available, then the performance will be hindered. This motivates future work to make the WASABI description more robust to segmentation noise. Thank you for your attention, and feel free to reach out if you have any question. You can check the code on my GitHub and also reach out there. Thank you.